Okay, so this is going to be the second video covering the material in Chapter 12. We're going to break this chapter into quite a few different videos. There's just so much to talk about with regression analysis. What I'd like to do in this video is kind of jump into an example, a fairly simple example, I hope, with just a few data points so that we can get an idea for the mechanics of how least squares regression is actually implemented. So the example that I'm going to cover is the example of Reed Auto. And Reed Auto, they run these week-long sales. And the weekend before they have the sale, they run a certain number of TV ads. And they want to know how effective these television ads are and what's the impact of running one additional television ad. So it should be clear to you that it's important that they run a different number of TV ads across the different weekends in order to uncover the relationship between TV ads and the number of cars sold. And they've done that for us over 5 previous sales. And they've collected the following data for us to analyze. Here's the data that they're asking us to analyze. So just to kind of jump into this very simple data set, simple because it's a nice small data set, you'll notice that if they run one ad here, the first observation in the data set, they sell 14 cars. Okay, so this is the way the data set is constructed. I wanted to point out to you that, later on in the fourth sale that they ran, they also had just one ad, but they sold 17 cars. Okay, so 14 and 17 seem reasonably close to each other to me, but they're not exactly the same number of cars sold when they run one ad. Why? Well, because a piece of this, we hope at least, that a piece of this relationship between cars sold and number of ads run is predictable, but it's not going to be completely predictable. Every time we run one ad, we could get 17, 15, 14 different cars. We're not going to get exactly the same number of cars every time because of that error term, right? This is statistic and it's an unpredictable world. Same is true for 3. I ran 3 ads in the second sale and I sold 24 cars. I ran 3 ads in the last sale and I sold 27. Again, they seem reasonably close to each other, but they're not exactly the same because of the error term. The average number of ads run on television is equal to 2. So it's the total number of ads run divided by 5. And then the average number of cars sold is equal to 20. Okay, so 100 cars sold total in the data set divided by 5 different sales. That's an average of 20 per auto sale. These averages and sums and the data in this table can be used to implement the least squares formula from the last video lecture. So I could take each one of these TV ads, I could subtract out, X bar, right? I could do the same thing. I could take, for the Y variable, I can take each observation and subtract out 20 from it. And I could take the mean of X and the mean of Y, and I could put all that information together in order to estimate the following equation for beta 1. So now I would encourage you actually to maybe pause the video and go back and do this on a hand calculator. It's pretty simple. But you should be able to really just in a minute or two convince yourself that if you take the deviation of each X value from its mean and Y from its mean, you multiply them together and add that up across all of the different observations in the data set, you'll get 20, right? You'll get 20. And if you take each of the X variables and you subtract out the mean and you square the result and add up all of those results across all the observations in the data set, you'll get 4. So our slope parameter is equal to 5. And then we know that if we have our slope parameter of 5, we can go ahead and calculate beta naught, or B naught, our estimate of beta naught, by plugging in Y bar and X bar to this formula. We know that because the regression line passes through Y bar and X bar. We talked about that in the previous slide. So we've got 20 as our average number of cars sold. 2 is the average number of ads, so we plug those in, and we get an intercept of 10. So here's our estimated regression equation. Right? The predictable part of the relationship between Y and X right? Y hat and X. Y hat is equal to 10 plus 5 times the number of ads that are run on television. Here's a picture of it, okay? So in terms of interpreting the results here, we've got a 5. That means that every time, since that's positive, every time we increase the number of ads on television, we sell more cars. And in fact, the model predicts that every time we increase ads by 1, we're likely to sell 5 more cars. That's our best guess as to how many more cars we'll sell if we run one additional ad on television. Of course, we're not going to always sell exactly 5 more cars if we run an additional ad because of that error term and because not the relationship between cars sold and TV ads isn't perfectly predictable. Okay, but that's our estimated regression line. You can see that the different data points around the estimated regression line don't fall exactly on the regression line. We wouldn't expect them to. But the regression line using our least squares technique does seem to pass right through the center of the data. It does because it minimizes the sum of the squared deviations of the data points from the regression line. That's the whole idea behind the least squares method. Okay, so we've gotten to the point here now where I think we've built up enough background for you to jump in and do a little bit of work on your own. For this piece of the checkpoints for chapter 12, I've put together a nice description of beta analysis for you in chapter 12 worksheet for video lecture checkpoints. I'd like you to open that and read over it. I'm going to ask you to complete what's called a beta analysis. So you're going to want to open up the dataset betaanalysis.xlsx, open that up, and you'll see the data that you need to complete the worksheet. You're going to be asked to do this regression analysis on your own in Excel after you've opened up that spreadsheet. So you might want to review the Chapter 12 notes and Excel guide. At the end of those notes, there's a guide to how to do simple linear regression analysis in Excel. We're getting to the point now where the computations are complex enough, particularly with a large data set, that it's harder and harder to separate these questions from the Excel piece. So these are going to kind of start to come together in these checkpoint questions. So the analysis is getting fairly sophisticated in this class now. Let me tell you just a little bit about beta analysis before you jump in. Beta analysis is a technique that's used a lot in finance, and a stock's beta is something that is a key component of what's called the capital asset pricing model. So what we're doing here is actually a really nice application of simple linear regression analysis. Basically what you do is you take a stock, and the example you're going to work through is going to be McDonald's stock, and you look at the percentage change in that stock price over a number of different periods, okay? And then you ask, how volatile is that change in the stock price compared to a broad market index? So to do a beta analysis, you just need 2 variables. You need the change in the stock price, and then corresponding to those changes in the stock price, you need the corresponding changes in a broad market index. Your changes in the stock price, for us McDonald's stock price, that's going to be your dependent variable, and your independent variable is going to be the change in the broad market index. And so you're going to do a simple linear regression with McDonald's stock prices, the change in them. On the left-hand side, that's going to be your dependent variable, and you're going to look at how that varies with changes in the broad market index, the price associated with the broad market index. If you end up with a slope coefficient that's bigger than 1, then we would say that McDonald's stock is a relatively risky stock, because it tends to fluctuate more than 1-for-1 with the broad market index. Broad market index being a nice diversified portfolio. Okay, if you end up with a beta coefficient that's less than 1, then it would look like stock. We would say that McDonald's stock is a relatively safe asset to put your money in because it's less volatile even than the broad market index, which is a nice diversified portfolio. In that Chapter 12 worksheet for video lecture checkpoints, I've given you a really nice full description of beta analysis and a link, I believe it was to Investopedia, which has a really nice description of what beta analysis is and what it's used for. Okay, so go ahead and open up take a look, read carefully that worksheet, open up the chapter 12 notes, make sure you know how to do a simple linear regression analysis in Excel, and open up that data set and answer the following questions. Okay, welcome back. We're going to take a brief diversion from our read auto example to talk about the sum of squared total regression and error. These equations look a little bit cumbersome, but I'm going to show you a graph next which will make all of this very clear. But for the sake of completeness, I'm going to give you the equations right here. Not the type of things necessarily that you have to memorize, but you should at least, when you see them, be able to understand and explain them. The sum of squared total is the total sum of squared deviations of y from its average value in the data set. Okay? I mean, it's that simple. You take each observation, subtract the mean, see how far away it is from the mean, square it and add it all up, and you have the sum of squared total. The sum of the total squared deviations of the dependent variable from its average value in the data set. Now, what's important is that that sum of squared total can be broken into two parts. What we call the sum of squared regression, sort of that's explained by the regression model, and then the sum of squared error, the part we can't explain. Okay? And so the sum of squared regression is calculated by taking the fitted value and the difference between the fitted value and y bar. So you kind of start at y bar, and then you go up to y hat, right? That tells you the amount of deviation from the mean that's explained by the regression model. Take that for each observation, square it, add it all up. You have the sum of squares due to regression. And then once we're at y hat, right, we move from y hat to the actual realized value of y. That's the part of the difference between yi and y hat that's not explained by the model. It must be due to the error term. Okay, we calculate the difference between that y hat and yi for every observation of the data set, square it and add it all up, and we have the sum of squared error. So if this looks at all confusing, I think that this simple picture will make it all clear for you. Okay, we've got one point that I've highlighted, and this point is going to just be an illustrative point. We're going to look at its contribution to sum of squared total, sum of squared error, and sum of squared regression. So clearly, this distance is a sum of squared total. The green line here is y bar. That's the average value of y in the data set. And this is the predicted value of y, and here we have the realized value of y. So the difference between y bar, okay, and the realized value of y is the total deviation of y from y bar. We would take the difference between the two and square it, and that would give this observation's contribution to the sum of squared total. Okay, and that contribution could be broken down into two parts. Right? The first part is the sum of squared regression. Clearly that is equal to the difference between the predicted value of y, because we're right here. We're on the regression line, so that's y hat I. Right? Read that right here. Go over to the left, to the vertical axis, see that's y hat I minus y bar. We square that, add it to all the other squared deviations of y hat from the mean, and we get the sum of squared regression. So this is, this distance here that I'm highlighting is this observation's contribution to the sum of squared regression, and then everything that's left over is attributed to the error, the sum of squared error. And that clearly that's the difference between the realized value of y and what we found on the regression line, y hat I down here. Okay, that's what's left over. So this represents, the part that I'm highlighting here now, represents this observation's contribution to the sum of squared error, SSE. And it's clear from the graph now what I said before, which is that SST is equal to SSR plus SSE. Okay, and that's an important relationship. It's important for a number of reasons, but right now we're going to really look at what's called the R squared. We're going to dive more into ANOVA and the F statistic when we do a multiple regression analysis. I will say this chapter in your textbook talks about the F-test with simple linear regression, but we're going to talk about the t-test, and the F-test is redundant if you've covered the t-test with simple linear regression. In fact, the F statistic is nothing but the T statistic squared. So we're going to save a more complete discussion of the ANOVA table and F testing for the multiple regression chapter. But what we have here is R squared, called the coefficient of determination. And what it is it's the sum of squared regression. So that's the deviation of the value of y from its mean that's explained by the regression model, divided by SST, which is the total deviation of y from its mean squared, and add it all up, this total sum of squared. So what the R squared measures is the percentage of the deviation of the mean that's explained by the regression model. You could think of it that way, okay? So obviously, higher R squareds are preferred to lower R squareds because it means that our model has more predictive power and it fits the data better. You have to be careful, though, a little bit with R squared. I'll give you a couple of warnings here. First, R squared is a purely descriptive measure. So it's not necessarily true that you have a model that doesn't capture a true relationship just because you have a low R squared. With economic data in a cross-section, it's not unusual to have a really good model that explains an important economic phenomenon, but to have an R squared of 0.3, where 30% of the deviation of y from its mean is explained by the structure of the model, the predictable part of the model, but a lot of the variation is still left unpredictable. Okay, and so having a low R squared doesn't necessarily mean you have a bad model. Again, this is an inference. This is just a descriptive statistic, so you have to be careful there. Also, you might be really tempted to compare R squareds across models. That's okay as long as the models have the same dependent variable that are measured. It has to be measured really in the same units and with all the same transformations. If you're comparing two different R squareds across models that have different dependent variables, the comparison is really meaningless. So sometimes R squared is misused that way, and I want to make you aware that it can be misused and abused in that way. Okay, so be careful with your application of R squared. Still, the coefficient of determination is routinely reported by regression packages, and it's an important piece of assessing how well a model fits. So I'm going to show you the calculation of R squared for our read auto example. Remember that our read auto example had the equation that was estimated, that was y equals, it was 20, was it 20? Or well, we'll figure it out in a minute. But I remember that the slope was equal to 5. That I remember. So we could figure out what the intercept was here. If we've got 3 adds, 3 times 5, that would be 15. So to get to 25 would have to add 10. So the intercept must have been equal to 10. Okay, I'd forgotten that, but it's easy to figure that out. So what I'm doing here is I'm going to take each one of my adds, okay, and I'm going to plug it into that estimated regression equation. So in other words, 10, right, plus 5 times 1 add would be a predicted 15 cars sold. So that's y hat I. I do that for every observation. Okay, but let's just look at the first observation here. So that's y hat I. I take the actual number of cars sold minus the predicted. That's going to be minus 1. Okay, 14 minus 15 is minus 1. I square it, and I get a 1. And that is the first observation's contribution to the sum of squared error. Okay, I do that for every single observation in the data set, all of them, and I add them all up, and I get the sum of squared error, and that's equal to 14. Now I'm going to do something similar here for the sum of squared total. So for the sum of squared total, what I'm going to do is I'm going to take each one of the observations, yi, and I'm going to subtract out y bar. Let's look at a different observation for this one. Let's look at this observation, the third observation. We ran 2 adds. So 2 times 5 is 10. 10 plus 10, right, that's 20. So the predicted value is equal to 20. We actually sold 18 cars, but the predicted value is equal to 20. Okay, so if I take the actual number of cars sold, 18, so that's right here, 18, and I subtract out the average value. So I need the average. I'm going to go down here, recreated the average here. The average number of cars sold across these 5 different sales is equal to 20. So I'm going to take the difference between the 18 and the 20. So minus 2. Then I'm going to square it. Minus 2 times minus 2 is 4. And I get the third observation's contribution to the sum of squared total. I do that exercise for all 5 of my observations, and I add them all up, and I get the sum of squared total. And that's equal to 114. Okay? Now remember that the sum of squared total is equal to the sum of squared error plus the sum of squared regression. So in order to get the sum of squared regression, I just take 114 and I subtract out the 14. And I'm left with the sum of squared regression. That goes in the numerator of my coefficient of determination. Sum of squared total in the denominator, that's 100 divided by 114 for an R squared of 0.8772. That means that 87.72%, let's call it 88%, we'll round it up, roughly 88% of the deviation of y from its mean is explained by the regression model. Pretty high R squared. It looks like we can explain a lot of the variation in the number of cars sold by looking at the number of ads that are run the weekend before. Okay, that's how you interpret the R squared in this case. So the last thing I'm going to talk about here before we take a break again is just the assumptions of the model. And I'm going to talk first about just these first 4 assumptions. So these are really critical assumptions. And what they lead to is the result that ordinary least squares is what we call unbiased. So if we want beta naught to be, if we want B naught to be an unbiased estimator of beta naught, so that B naught on average estimates beta naught correctly, and B1 on average estimates beta 1 correctly, right? We know what unbiasedness is. We've talked about that before. If we want those parameters to, those estimates, least squares estimates, to be unbiased estimators of the population parameters that correspond to them, we need these 4 assumptions to be satisfied. The model that we've specified that's linear in parameters needs to be an accurate description of the relationship between the variables. We need that. Of course, we saw the formula for beta 1, and we know that you need to have variation in the x variable in order to apply that formula. Basically, what's going on there is if you want to uncover the relationship between the x variable and the y variable, then you got to vary the x variable. Otherwise, you're not going to be able to uncover the relationship. How can you talk about the relationship between car ads and TVs sold if you never allow the number of advertisements on TV to change so that you can actually map out and uncover that relationship? So without getting too technical, that's what the second assumption here refers to. Sampling is always important in statistics, so we're going to assume here that we have a randomly collected sample. We don't have any biases that are introduced from sample selection bias. Now, in the real world, sometimes you have the data you have, and this becomes an issue. And there are advanced econometric techniques for not correcting the data, but once you have the data you have, actually correcting the estimation techniques. Again, beyond the scope of this course. For the 4th assumption, we need no correlation between the error term and the x variable, the independent variable in the model. So we state that as covariance between E and X is 0. Sometimes it's called the zero conditional mean assumption. I think the easiest way to explain the significance of this is to give you, an example of when it might be violated and why. Let's suppose that we run a simple linear regression model, we run a simple linear regression model, so we only have one dependent variable. But there's really another dependent variable that's important for explaining the dependent variable as well. So I'm going to try to make something up here that works. Let's suppose that we've got the car ads as our independent variable, and we're explaining the number of cars sold, okay? And let's say that there's also another variable that explains the number of cars that's sold. And that is, the health of the local economy, okay? And so let's say that it just so happens that in the data set, and this could just be accidental, but in the data set, we tend to run more ads when the economy's healthy than we ran when the economy wasn't doing as well. Okay? And let's say that we could proxy the health of the local economy by the local unemployment rate. Okay? But we left the unemployment rate out of the model. If we left the unemployment rate out of the model, then naturally it's sort of absorbed in the error term. And that's going to cause the error term to be correlated with the X variable. Since when the economy is doing well, right? At the same time, those are also times when we tended to run more television ads. So now we've got this correlation between the error term and the variable that we have included in the model, which is TV ads. And we could correct this by appropriately adding the unemployment rate into the model, which we'll do. We could do with the techniques from the following chapter, but we would have the model misspecified. And we could attribute some of the impact of the health of the economy on auto sales. We could be attributing some of that to the advertising campaigns, right? And we would bias our results, okay? So, we need to really have a properly specified model. And we're going to talk a little bit about that. We could literally teach more than one full course just on the specification testing of regression models. But I'll show you some fairly simple techniques at the end of this chapter. So if that's satisfied, we have unbiasedness. And if all you want to do is predict with the model, I mean, if you're doing some type of a data science project and you're using the algorithm just to kind of classify things, right? You want to use a regression-based type of an algorithm just to classify things and put them in the right classification or prediction, make a prediction. You're okay with unbiasedness. You don't need the additional assumptions to be satisfied. In economics, we're usually, in business oftentimes, we're looking to do a little bit more than that oftentimes. We're looking to do, we're looking for both efficiency and to do maybe some inference and some hypothesis testing. And if you're going to do that, you need a little bit more. You need the error term in the model to have a constant variance. Sigma squared is what we typically call the symbol we use for the variance of the error term. We need that to be constant and unrelated if you have time series to other values of E. So we call that the assumption of, I'm going to give you a big word here, homoscedasticity, okay? Homo equals scedasticity errors, equal variances, scedasticity. If that's violated, we call it heteroscedasticity, right? Different variances, hetero, different, okay? So if that assumption is satisfied, then we can state that OLS is even more than being unbiased. It's blue. It's the best linear unbiased estimator. In other words, not only is it unbiased, but it's efficient, has a minimum variance. That's really a nice property, okay? So, but we need assumption 5 to be satisfied to state that. Okay, now, assumption 6 concerns the error term. And your textbook states that the error term should be normally distributed in order to do hypothesis testing on beta naught and beta 1. That's almost correct. If you have a small sample and you can't use the central limit theorem, then the dependent variable and the error term should be normally distributed, right? They should be normally distributed if you have a small sample and you want to do, t-tests and that type of thing, okay? Coefficients will follow t-distributions exactly if the error term is normally distributed. Okay, this is a lot like our discussion of the central limit theorem when we did hypothesis testing and talked about the sampling distribution of the mean and the sample proportion. Same thing that's going on here. I do want to point out something your textbook leaves out, and that is that you don't need assumption 6 to be satisfied if you have a large enough sample. Okay, there are what we call regression asymptotics, like really, really big samples. If you get it doesn't have to be that big, but if you have a large sample, the central limit theorem will kick in terms of the sampling distributions of B0 and B1, just like the central limit theorem kicked in when we talked about the sampling distribution of X bar or the sample proportion. And you'll be able to use z-scores and the standard normal table in doing hypothesis tests based on the central limit theorem when you do regression analysis if the sample size is large enough. Okay, so we're going to take a break here again. There's a lot of material in this chapter, and we'll see you in video 3.